So binary search is just like reducing a search space by half every time. So when you have this LR, you check for the middle and divide the parts into two to search, right? So each of the halves that you will search next will be half of the original size, because you are doing the search at the middle and then dividing into halves, right? Almost the middle. So it will be like the range size by 2, see something like this, right? Or in fact range size minus 1 by 2, because you check the middle and then you go to the left or right. So range size minus 1 field over 2, right? So this will be the maximum range size that you will have after one iteration. So every time it almost gets to half, so you need log n number of iterations, okay, log base 2 n number of iterations to search for any element in a sorted array. Okay, so this is a very standard form of binary search, but binary search is much more powerful than just searching for numbers in sorted arrays and things. But is this clear to everyone? Like, how are we doing this search on a sorted array? This should be clear to everyone that you have a range L to R to search. You check for middle. Based on this middle value, you go toward, you change your range either to, like, let's say this L dash to R dash, or this L dash to R dash, or this is the answer. Is this clear to everyone? I think this should be good with everyone. Can I have a +1 on the chat if this is clear to everyone? If you have any doubt, make sure you're writing that on the chat. Okay. So we'll be talking about implementation a bit later after we talk about few more problems, like just some general ones, and then we'll be showing you how to like code a binary search in a like a very favorable way. And what I mean to say as favorable way is a coding style that you can follow for any binary search problem, and it should work like a charm. Let's look into how we can use binary search into more difficult problems. So before we move into more problems, you need to understand a concept of monotone space. Okay. So space, by space I mean to say a space of solution potential. So I mean to say, let's suppose in a array, the array that we discussed where you had to search for element, the solution space was nothing but the indexes, right? You had indexes in an array. Okay, let's say you are searching on the number line, so the space is the real number line space, right? So whenever you have a L to R, what is the thing that you are searching on is called space. Okay, that's just a definition. Like that, the space is on what values are you searching in the binary search. Okay, now for a binary search to hold, the space should be monotone. Now what do I mean by monotone? So you should have some particular function f of x, okay, that should map every item in this space to either a yes or no. Okay, okay, so there should be a function f of x which will convert every element in this space to a yes no, and that space is called a monotone if there exists f of x for that problem such that it makes it a bunch of yes, okay, followed by a bunch of no, okay, or a bunch of no's followed by a bunch of yes. Okay, so these are both monotone spaces. Like there are a lot of yes, then a lot of no's, there are a lot of no's, and then there are a lot of yes. Okay, so every index, like whatever the value over here is, or this index, you pass into some function and it converts into a lot of yes, a lot of no, then it's a monotone space. Okay, so we will understand what this is through an example next, but this monotone space can be of the form something like this as well. Can the ni's be mixed? No, y and n's cannot be mixed. So this is a valid monotone space. Okay, all n's are also a valid monotone space, but this is not a valid monotone space. Okay, this is not a valid monotone space. Like there should be a rigid partition between the yes and no. That's what I'm saying. Okay, this is something that should be identifiable. Okay, some distinct boundary between yes and no, and beyond one side there are all yes, and after that there are all no's. Okay, if if this kind of boundary can be created using a function like which maps these indexes into yes and no's, or any search space into yes and no, then that particular space is monotone space, and we can use binary search in any such problem. Okay. Now, don't worry if you're not 100% clear about like what is this f of x, how are we doing this. We will understand all of these through examples. But just understand this, that after some f of x transformation on the indexes that you're searching on, or the values that you're searching on, it should convert it into a bunch of yes and a bunch of no, or a bunch of no's and a bunch of yes, such that there is a rigid partition between these two spaces. Okay, that's all is needed in a particular problem to be, for binary search to be applicable in that. Okay, is this clear to everyone? Like this yes and no concept, like at least there should be separable, right? That's all you need to understand. Okay, so can you move to the next thing then? Let's now understand using a quick modification of the problem that we discussed. So you were given a sorted array and you had to search for the element, right? Let's say you are given a sorted array, but that has been rotated by some particular value x. Okay, so ideally, let's say there was 1, 2, 3, 4, 5, 6. Okay, so let's say after some rotation, the array given to you is 5, 6, 1, 2, 3, 4. Okay, something like this is given to you in an array. Okay. Now you need to find out how many times this array was rotated. Like this was rotated 2 times, right? After 2 rotation of this array, by rotation I mean to say take the last element and make it the first. Okay, this is 1 rotation. So after 2 rotations, you will see that this is the final state, right? Now the question is, you are given this final state, find out the number of times the original array has been rotated. Okay, make sense? Is the question clear to everyone? Like this array is given to you and you need to find like how many rotations there was made. Okay. And like this array is of size n, and you need to, like, given this array, after this input is taken, you need to solve this in better than order n. But like obviously we would try to do something like a binary search or something, but like we need to search for this like rotation point, rotation value by some binary search idea. Okay, so how do we try to apply binary search in this kind of problems? Let's understand that. So if we look at the values, what do we have over here is there is some increase in value that's happening. Like there is an increasing value because this array is sorted. So if you rotate, let's suppose some k indexes from the last, those k indexes will be at the front, and then the first n minus k indexes will be at the end, right? This is n minus k and this is k. Make sense? Now this k was sorted initially, so this will remain sorted over here, and similarly this was sorted, so this will remain sorted over here, right? Now only thing that happens is there is a break between these two elements over here, that okay, this element becomes less than this, rest everything is sorted correctly, right? So if we can somehow find this particular element, it would be like this particular element where like the first time this property gets break, like this sorting property, then we can easily find out how many times it was rotated, right? So we'll try to do that particular thing over here. So let's understand how are we doing this. We will try to use a monotone space concept in this particular problem. Okay, so now let's like quickly write it more. So 1, 2, 3, 4, 5, 6 was there, and we had 5, 6, 1, 2, 3, 4, right? So now we want to search what is the index of the smallest element in this particular array, right? That is what if we can find that, then we are done with the problem, right? Because if this is at 2, then we know that we have rotated it by 2 values. Is this clear to everyone? If the smallest index is at the 2, then we know that the array has been rotated by 2 value. Is everyone clear with this? Yeah. Okay. So one more thing, in this problem we assume that yeah, this particular array has all distinct elements. Okay, like elements are not same for now. Okay. So now we need to find this particular smallest element in this. So how do we search for this smallest element in this rotated array? So now this is the array and the indexes are 0, 1, 2, 3, 4, 5, right? So we will try to search on the index. Okay. So this will be our solution space on which we will be searching. Okay. So we will try to create a function which will convert this space into a monotone space. So such that whatever we want to find comes close to the boundary. Now, why do we want this to be one of the boundary elements? Let's understand that going back to this. Okay. Now, let's suppose you know that the monotone space follows a lot of yes and a lot of no's. Now, suppose you want to find this first no in this array. Okay, this space. You know that this is y, 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 and then n, 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 n. Okay, you need to search for the element which is the first n. Okay, so in this we can easily use a binary search because this would be L and R. So you search for, you see an element. Whenever you see a yes, you know that you need to go to the right. Whenever you see a no, you know that either that's the answer or you need to go to the left. This makes sense to everyone? That if we had to search for the first yes in this array, it's very easy to be done using a binary search. That if you see a y, you know that all n's are after y's for this particular space, so you go towards right. If you see a n, then you know that either that n is the last or the n will be somewhere towards the left. Okay, so over here as well we will try to make this some sort of like boundary n or y. Okay, anyways, like the naming n and y does not matter even if we swap the values, but it's just that that rigid boundary should be present. Okay, so let's try to create a function. So let's suppose this x would be ARR of x is equal to ARR of x is greater than ARR of 0. Okay, let's say we define a function something like this. Okay, so let's call this greater than equal to 0. Okay, yeah, let's define a function something like this. So now if we talk about the values now, what is the value of f of x when x is equal to 0? So 0 maps to, this is true, so y, 1 maps to y, n maps to 0, no, 3 maps to no, 4 maps to no, 5 maps to no, right? So as you can see, this is like a monotone space transformation that we are building using this f of x, right? So now we just need to search for the first no. Okay, so for that we use the same strategy that we talked about a bit earlier, that every time you see a yes, go right. Every time you see a no, either that's the answer or go to the left. Okay, is this part clear? How, like, this is a f of x for this particular problem. Is it clear or not that this is converting this particular into a monotone space? Yeah, so this is like a transformation function for this particular problem that will convert this problem into a monotone space. Okay, so let's quickly look into one of the codes so that after this you can understand how are we, like, even if we talk about how are we implementing this, you can understand, okay, this is what we are doing, right? So we will try to like solve the same problem. Like, you are given an n, that is the size of the array, and other function possible. Yeah, a particular problem can have other functions as well. You can compare it with the help of last value as well. Like if you want to, something like that, ARR of x is less than equal to ARR of n minus 1. This is also possible in this particular problem. So in that case, if you see the mapped values, it will be no, no, then yes, 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 right? So in that case, you have to find the first yes, something like that. But this is not correct. Let me give you one particular function. This is not correct. ARR of x is greater than ARR of greater than ARR of x minus 1. So if you transform using this, what you will see is you will get, okay, trivially we take this as yes, then this is of course yes, but then like after 6 to 1, it will be, when you see 6 to 1, it will be no, then it's yes, 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 right? But this is not a monotone space, so you cannot use binary search in this, right? So we will be using some function that transforms this into a monotone space. Okay? So let's understand first of all, how do we write a binary search neatly every time so that you don't make bugs in implementation. I would highly recommend using the style that I'd be using right now, because this is quite tested and it works really well without any bugs in a lot of different problems. I have seen a lot of people using some other formats and like getting bugs due to the problem in format itself. So make sure you are following this particular syntax only. So in binary search problems, a lot of time we need a f of x, right? This f of x is needed. So we define this f of x a lot of time in a global scope. So what we do is we keep the variables as well in, let's say, global scope as well. Okay? So you can pass them by function as in the parameters of function as well if you want to, but just for simplicity, let's keep things in global scope. Okay. Now we have the array and we want to search for the breakpoint. So what we will do is we will write a binary search. So for binary search, we will have three variables right now. Low equal to the 0 and integer high will be equal to n minus 1, right? So note that this is the space that we are searching. From 0 to n minus 1, anything can be the answer. So out of these, one of these answer, and we need to search this. And we know that this space, this index that we talked about, follows a monotone space values, right? Like monotone space after we apply a transformation function. So this is the space we would be solving the problem in. And we keep an answer variable to keep track of the position where we find the first yes. So if there are no answers found, then we will keep it like a -1, like there is no answer. Or if we find a if you find a no, which is like where we have found the particular uh, first no or something like that, first no, then that's the answer. Okay, so let's keep it. So you can keep this like, so how do you initialize this answer? We will discuss just a minute later after we complete this, and we discuss how you be what should you get when the array is completely sorted. So let's talk about how you will write the rest of the code. So you will write while low is less than equal to high. So while there is some finite space left in the low to high range, okay, keep doing. So you need a middle value, which is low plus high by 2. Okay. Now if check of mid else. Okay, so now this check of mid that we are writing, this mid is our x and check will be our f of f function that we talked about. Okay, so I'm just writing the name, I'm just changing the f function's name as check. Okay, so this will check whether it's a yes or no. Okay, so we define a check function for a particular index and that will give us whether it's a yes or no. Okay, and based on that we will move somehow. Okay, so what is our check function? We just return quickly ARR of x is greater than equal to ARR of 0, right? This is our check function. Make sense? Now if our checks return true, that means ARR of x is greater than 0. So we know that this is a y, right? So if it's a y, we know that we need to go to a left side. So we make our low equal to mid plus 1. Okay, or else if our check returns no, like it's false, that means it's a no. So either that will be our answer or our answer will lie towards the left. Okay, and that's it. Okay, high equal to, oh sorry, this uh, oh sorry, this should be mid -1 and this should be high, right? Oh, sorry. That's a typo. High should be if mid is yes, then we make, sorry, if we have check mid, this would be low equal to mid plus 1, or else it will be high equal to mid -1. Yeah, this should be correct, because let's understand what we are, why, how are we writing this. So if you have some L2R and you check the mid, if this is yes, then you go towards right, because you know this is a y and then n space, right? This is how the space is distributed. Okay, so we go towards the right. That's what is being done in this first part. Okay, and or else we do this, right? Is this clear to everyone? What are we doing? How are we moving our check low and high? So let's say we give it the same input 561. Yeah. So it should give us 2 because when it's like when it's searching for the element, it will give us 2 because like this is the index that it will stop at. So answer will be equal to 2. So we get the answer. Okay. So now, what if there is no breakpoint? Like what if everything is, so we are searching for no, right? Now, what if there are two possible cases that can happen? What if it's all yes, or what if it's all no? So in case of all yes, what should be our answer? And what in case of all no's, what should be our answer? These are the two things that you will have to take care in the code. Based on that, you will have to initialize the value of answer. Okay. So if it's all no, then by default our code will work and it will find us the first no, and that is okay because if it's 1, 2, 3, 4, 5, 6, and if this is some like this will not happen in particular for this particular problem, but okay, even if it happens, it will find us the first element. Okay. Now what happens when you get something like this? That means if you take the array sorted, okay, 1, 2, 3, 4, 5, it will actually be all yes, right? Because everything follows the condition. Everything is greater than or equal to the first element. So in that case, there is no first no. So this part will never get executed. So answer will never get initialized to something. So in that case, you will have to trivially assign it to something that works. So for all no's, you know that for all yes, you know that you need to initialize it to 0 because if it's sorted, then you have to rotate it by 0 value, right? So that's why we have initialized the answer to be 0. Okay. So now in this particular code, whenever you are like writing this binary search, there are three things that you will have to think about. One is this initialization of ranges and answer. So it's like what range are you searching in for the answer? Like what is the solution space? Okay. How do you move the lows and highs? So this is guided by two things. Is it like yn space or a ny space? Okay. And whether do you want to find the last y or first no, depending on that, these you should change the logic. Okay. How do we initialize? Okay, so this low and high is initialized as the range in which you will have to search for. Like this is the indexes in the array. Okay, this answer is initialized based on what if this particular answer never gets like updated in this particular loop. Like you are updating your answer over here, right? What if this particular portion is never executed? That means always check is true. That means always it's all wise. So in that case, what should be the answer? You initialize it with that value. So if it's all y, that means that corresponds to the case where it's sorted. So in that case, the answer is 0. So initialize it with 0. Okay. So sorted case will have answer 0. So that's why we initialize it answer 0. All y case. Okay. So now this range part. Okay. Then this search movement part where you like whether you make low equal to mid plus 1 or you make high equal to mid minus 1. Okay. These are the two things that you will have to take care of. And the other thing is, of course, the check function that we wrote over here. So that is like the constructive part of every binary search problem. So most of the binary search problem that you will solve you will just need to think about, like the thinking part will come in the construction of the check function. How do you design a efficient check function that will work with the problem, and like you will be able to like get the boundary. Okay. So this check function is the third part. Okay. So initialization of the ranges, movement values. How do you movement based on like its yn? So you will have to think in terms of like, is it a yn space or a ny space? And based on that, which side I move. That's something like you can write on a notebook and think. Okay. And the third thing is this check function that you write. Okay. Is everyone clear with this code? Like how is this code working? Any doubts on this one? How can I judge that a question can be solved with a binary search? You will have to, so first of all, so you will have to think about these things. Can you find a check function, and is it a monotone space? Like, is it a monotone space, and can you design an efficient check function? So if these two are true, then you can apply binary search. So identification of problems comes with looking into constraints, like thinking about solution in that direction. Like, this is a general problem, right? How can you decide on which algorithm can be used for any problem? So this is like a general problem. this you will have to try on each of them mostly. Like you should get some intuition. Okay, this can be solved with the binary search. Then should I like let's try let's try and do some progress. Okay, it's not working. Let's track back and try DPS, something like that. So it's a general thing. So how one algorithm can be applied to a problem, that you will get hints from constraints, because binary search are mostly like of 10 to the power 5 size arrays, or searching on 10 to the power 5 size array. That's the most frequent one. Uh, Apart from that, even some things when you need things in log and binary search is the thing to go. So that you identify through solving problems. Okay, once you solve a lot of problems, you start to recognize the pattern. Okay. But this particular style, make sure you're following this particular style, like these three variables and this particular syntax. Okay. Makes sense? Anyone having any doubt on this code? Okay. Nope. Okay. Then if there are no doubts on this code, then we can move to next thing. That is, how do you decide on the complexity based on the f of x function and array space? Okay. So let's suppose you are having a range L2R, okay, and you have a check function f of x, okay. So what is the time complexity of this particular like binary search if you apply using these two things? Okay. So for this, the complexity would be log of r minus L, okay, multiplied by f of x. Okay. Now why is this? So what is happening in binary search? We have an array, or we have a solution space, let's say, and we try for a particular mid. Okay. Whenever we see a mid, we want to know whether it's yes or no, right? So whenever we have to call for a mid, we check whether it's a yes or no. So to check for yes or no, we call the fx function to get its like y or n value, and based on that we move. So the movement part will take order log of like range space, and for every mid call you will need the f of x to be called, and that will like take the complexity of f of x, whatever the complexity of f of x is. Okay. So in this particular problem, if you think about the range space was up to order n. So r minus L will be n. So this will be order log n, and the check function was order 1, right? The check function was order 1, right? So this is order 1. So in this case, you can use this particular problem. Now note that what are the things you can use in check function? Okay, what are the things that you can use in check function? So over here we pass the mid value, right? What is the mid value? So for the check, you can use anything that is static. So check can use anything that is static, like the static array values, like we use ARR of 0, right? Because it's not changing. So anything that is static or the mid value, okay? These things can be used. You cannot use L and R in the function, like the space that you're searching in the check function. Like that's not how you generally try to do it. Like you can use the indexes positions, but you cannot use something like based on that, something that's changing, right? Like this check function might use some value that is inferred from L and R, like some array sums or something like that from L and R, but it should not directly use some like use this as L and R directly in the check function. So as you keep practicing more problems on binary search, you will understand what to keep in check and what are the things that you need in check. That comes with practice. But like generally, you can use anything that is static or the mid value that you're searching. Right? Mid obviously you need to pass. Like how do you check otherwise? Okay. So now let's move to the next problem. Then is everyone clear with this rotated array problem? That you have a rotated array and then you need to search for the breakpoint or how much it is shifted. And this is a very standard problem. Like this is like one of the most straightforward problems in binary search. But this is, so you could have solved it by using some other forms of binary search on this. But the thing is, once you start thinking about binary search in this monotone space idea, every problem becomes equivalent. Okay, every problem becomes equivalent. So now you need to just understand one concept to solve all binary search problems, right? So design a function, write a binary search with this function, and write the movement part. That's it. That's all you need to do in this problem. Is this problem clear? Can we move to the next one? Can I have a +1 from everyone? Everybody has understood this one. So let's next move to one more problem. So let's say we had like a function called lower bound, right? Remember lower bound? So now let's suppose you have an array which is 1, 2, 3, 7, 14, 21, something like this, 22, so on, right? And now you need to search for the first element greater than equal to some x given input, right? So let's call this some a because we are going to use x in the check function. But okay, find the first value which is greater than equal to a. How do we use this? So I hope you all know this by now that okay, lower bound gives you the index or the iterator to the element which is greater than equal to a in the array, right? So how do we design this using a binary search? What do we write as a check function? Can anybody please suggest on this one? Okay, yeah. So we would call this ARR. Let's call this ARR. Okay. So ARR of the check function contains the mid. Okay, this is x is mid, and this a you can pass this a because this a is static for the problem, right? For this binary search operation. So ARR of x is greater than equal to a. This truth value. Okay. So if you use this function, let's write the truth value. So this is, let's say a is equal to say 8. So this would be false. This is no, 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 then yes. Okay, then it's all yes. So now you just need to find the first yes. So the strategy would be like whenever you see a no, you go towards the right. If you see a yes, that either that's the answer or you go to the left, right? So you can simply implement this using the same idea. Okay. Is this clear to everyone? So now I hope all of you can implement a lower bound. Okay, so this will work in order login, similar to what the standard template library allows you to do. So now if you want, you can even write your own lower bound. Is this clear to everyone? Can I have a plus one? Because this is like the internal, like this is even is the same as how the internals work. Okay. Okay. Now let's move to the next problem. All y and all n. Okay. So it depends upon what we are searching for. Okay, let's move to the next problem. In that also we will face the same problem. Okay, so we will discuss that over there. Okay, Abhijit. So let's discuss about the next problem. We will discuss this idea of like what if there is all y and all n in this particular question. Okay, so let's suppose you are given an array and this is a bitonic sequence, bitonic array. What do I mean by bitonic array is it's first increasing and then it's decreasing. Something like this. Okay, does this make sense? Like it should first increase and it should first decrease, right? It can be something like this as well, like 12, 11, 10, like it's always decreasing. This is increasing and then decreasing. It can always increase as well, right? Like 1, 2, 3, 4, 5, 6, right? This is also a bitonic sequence. So this is one type of bitonic sequence. This is another type of bitonic sequence. There is another type. So by bitonic sequence, the definition is that there should exist some index such that before that index everything keeps increasing and after that index everything keeps decreasing, right? So you are given an input which is given to be bitonic sequence. You need to find the peak of the bitonic sequence, and by peak I mean to say it's the element which is the largest. Okay, can all elements be equal here? No, we are assuming the things that it strictly increases and then strictly decreases. That's a good point made. So it's strictly increasing and then it's strictly decreasing. Okay, so currently in the binary search domain, most of the things would be strict in most of the scenarios. Okay, so whenever we're talking about things like increasing or decreasing, just assume for this session that okay, we are talking about strictly increasing and strictly decreasing. Okay, So you need to find this largest element in the bitonic sequence. So of course we'd be using the traditional technique that we talked about just now. We need to design a f of x such that it converts this problem into a monotone space. Nice. Nice. Yeah, everyone is correct. Who's heard it until now. So let's talk about this 3, 4, 8, 12, 11, 4, 1, something like this. Okay. So this is the peak element. So what we design of f of x as is equal to ARR of x is greater than equal to let's call this greater than only because we know that it's strictly, so does not matter actually. ARR of x minus 1. Okay. So if we try to write the truth values for these, so first value we assume trivially that before it's minus infinity and after this is minus infinity. Okay. So trivially the first value we can put as y. Okay. This is y, and then this all is n, right? Now if we talk about this particular case where it was completely decreasing, so in this case this would be all n's, right? The other way around would be all yes, like it's 1 2 3 4 5, then it will be all yes, right? So these are the scenarios, and in this particular transformation we need to find the last yes. This is what we need to find. So the strategy would be same. As you see a yes, either that's the answer or move right. If you see a no, move left. Okay. So let's start with the code first. So we would be using the same code. We need to search index, so space remains the same. We'll talk about initialization now. First one y or n. So 12, 11, right? So this index, this takes an index. So if you put this particular index in it, this is false, right? So this is no. But so this would be, but this would be this comparing between these two values. So this would be yes, and we need to find the last yes, right? Okay, yeah, this, okay, yeah, this you can take yes, yeah, trivially, yeah, true, nicely pointed out, yeah. So this would be first one would be yes, and then all no's, right? And this will be all yes. So you need to find the first yes in this particular sequence in this L2R, right? So over here, this will be the answer because this is the peak element. Over here, this is the peak element. Sorry, I mean to say last yes. Yeah. So this is the, so there are no yes. So this is last yes, and this is the last yes. This is the last yes. So you need to find this peak element, right? So now let's move to the code quickly. So in this, let's keep this for now. We'll discuss this once because this might be confusing at times. So in this case, you also initialize it with 0 because if you don't find any last yes, trivially the first one should be the answer. Like if there is no yes, that means it's all no. So it should be the first one. But anyways, we keep it up to this. Okay. So we will change the things a bit to make the code simpler. What we will do is, if you observe over here, this first one is yes, this first one is yes, this first one is yes, right? So we will search in this particular range, okay, from 1 to n minus 1, and we will keep the answer as like trivially the first one is answer, and then we will search in the rest of the space. So what we will do is we will make the answer equal to 0 and search in the space 1 to n minus 1, right? So even if we don't get an answer in this particular space, we know the answer is 0, right? Make sense? Is this part clear to all? That if we search in 1 to n minus 1, if we find a yes, then like it's like better than what we have initialized it with. But if we don't find any yes in this range, then 0 by trivially is always correct, right? Because 0 will always work. Is this part clear? So just keep this as 0, search in space 1 to n minus 1, and then like we don't need to change anything over here, just this change like moving logic. Okay. So if we check a particular mid, and we need to change this check function. So let's write the check function first. The only thing why I did this particular change over here is to index, like to directly write this. So that this does not gets me a segment fault, right? Because or else if I write 0, this will become -1. So I have to handle that case separately, right? So just quick change to like make the code short. That's it. Okay. Now, when you are a particular index and it's true, then you know either that's the answer, and you move more higher, like right, or else it's not. If it's no, then you move, like you know that that's not answer and you need to look at the left side. So right, that's it, and that's done. Like the same style. Another problem. That let's look at one output, 1 2. So this will return us 2, which is the index of this particular element, right? So is everyone clear with this particular thing? Like how are we searching for the mid element over here? Okay. So now I hope you have got how it will work for 1 2 3 4 5. Yeah, sure. So 1 2 3 4 5 is all increasing, right? So whenever we check, we will get true, because every time we check for any index, it is like greater than the previous index, right? So for any index we check, it's always true. So so since we have not ran it like hypothetically on one of the cases, let's just quickly run it one. So 1 2 3 4 5. So initially answer is this is answer, and this is low, and this is high. Okay, and we want to search for the answer, so this will get to be the mid for first time, and the truth function for this is true. So we make answer equal to this, and we make low equal to this particular value. Okay, just a minute. I think right, and then in this range again, this is the mid. Now that is also true, like the function is true for that, so we make this as answer, and we make low equal to this particular value. Then again we check just this particular value, this is mid. For this as well it's true, so we make this as answer, and we like make low equal to this particular outside value, like there is no value over here, but we point the low to 6, like the index 6, and this is index 5. Sorry, this is index 4, this is index 5. So now this condition will fail, low is less than equal to high, so this will break, and this is our answer. We have saved it to 5, right? So that is why this particular like idea is used over here, this less than equal to, like low to high is the range that you are searching in, and unless it's completely exhausted, you like keep moving. And the why this code works in all the cases and some other codes does not work is like this particular statement, these two conditions. For this ensures that the space always gets reduced by at least one value. Okay, so this ensures that the space gets reduced always by at least one value. So this will terminate guaranteedly. In some implementations of binary search, people get a lot of TLEs and other things because it's an infinite loop. Okay, so make sure whenever you're writing, try to follow this particular style, because this is well tested and it works for a lot of problems. Is everything clear up to this point? Any doubts on up to this point? Can I have a +1 from everyone, and then we will move to some like. So these were all array searching based problems. Now we will start with like actual applications, like some good applications of binary search that appear in competitions. So now let's start with. So now this is the whole idea that you should be thinking for any problem that you start next, that okay, where is the space, how do I model it, what is my fx function, how do I do the search? That's it. Okay, so now let's talk about. So you're given, there is a integer line, like it's an infinite integer line. Okay, it does not look like a line, but anyways, so like there are like points at every integer value, like 0 1 2 3 4 5 6 7. So there are like this. So now, initially there are n points on this integer line, which is given, like their indexes are given, their positions are given to you. Okay, something like this. Okay, and you are given a value k, which is max number of points that you can insert. Okay, okay, so you can insert k at max k number of points in between as well, like anywhere in the number line as well. So what you have to do is, for any point in the number line, okay, for any point on the, like for any point out of these n, or any point that you place, the distance between that point to its closest neighbor should be minimum. Okay, let me explain this in a with an example. So let's say you have a point at say 1, okay, and you have a point at 5, you have a point at, let's say, 8. Okay, so if this is the state right now, like these are the points on the line, the distances that are present on the line is equal to 5 minus 1, which is equal to 4, 5 minus 8, which is equal to 3. So if this is the state, then the longest distance that is present is equal to 4, right? This is the longest distance between any two consecutive points. Okay, so my objective is to minimize this longest distance between two consecutive points. Now we have to minimize this using this k extra points given to us. Make sense? So I think now the question should be clear, that you have n points on the line given. You can place k more points at any integer you wish for. Okay, after placing those, so there would be, let's suppose you choose some y number of points to place, so there would be n plus y number of points on the line. Finally, out of the k, you choose some, you place y points, and after those, like let's suppose you placed a point over here, let's say at 3, then you need to print the minimum, so the maximum difference between any two consecutive points. Okay. So if you place a point at this 3, then the distance between these is 2, this is 2, this is 3. So the maximum value is 3. The maximum value is 3, right? So it decreased. It was initially 4, now it got decreased to 3. So what our objective is to place these k points in such a way that this maximum value is minimum possible. Okay. So if I, yeah, so let me explain this once more. I understand this is a difficult statement to explain, but let's say there are, so you have n points initially on the line. Okay, you have choice to place k points anywhere on the line. Okay, on any integer point, of course. After you have placed them, you will get consecutive distance, right? These are consecutive distances. Okay, if there are n plus k points in the line, then there would be n plus k minus 1 consecutive distances, right? Out of these, you find the distance which is the maximum. Okay, find the maximum distance. Okay, so this is the maximum distance currently. Okay, so you will have to place at most k points in such a way that this maximum distance is minimum possible. Like you have to minimize this maximum distance by putting k number of points, and after putting those k number of points, what is the, like if you do it optimally, what is the maximum distance point that you have to like find out. Okay, is this question clear now? Like there are few fixed points, place k more points such that this maximum distance becomes minimum. That's the problem. Okay. No, k is just a, like you can place k points anywhere on the line. It should be just an integer. It's not like fixed. So there are k points which are not fixed. Like you can place k points at any point on the line. And one more thing, on the line, at one integer point only, like at one integer value, only one point can exist. Like you cannot place 2 points at one particular value. Okay. Make sense? Is the question clear? Yep. So given n, so just repeating, so just think about it. So I'm just reiterating for if someone is not here. Given n fixed points, your give me your like idea on how you put at most k more points in between them, such that the maximum distance between any two consecutive points become the minimum. That's what you need to find. Okay. Greedily placement between largest distances. Okay, fine. That's a good idea. So let's take a scenario. Let's say. So I hope you got the. Yeah. Okay. That's a good idea. Nice. I think it's a. So let's say there are points something like this. Let's say there is a point at a 0 and at 100. Okay. So there is a gap of 100 between them, right? Okay. So now let's suppose you this maximum distance is 100, right? Now if you have to put 1 points, what you will do is you will put it in this 100 distance and make it split into two, right? 50 and 50, right? Now let's suppose you had to put 2 points in this particular scenario. So if you maintain a multi-set, if you do a greedy strategy, what you will do is you will put 1 point on this, make it 50-50, and then you will pick the larger one and then put 1 point in this. So it will become 25, 25, and 50, right? But that won't work because you could have put 2 points together on this one. So like incrementally putting 1 by 1 points is not ideal in this particular case, because if you put 1 point it will split, but if you put the next point on the same range it might change the idea, right? So it might seem trivial that okay, why do I not put two all of them in this, but the thing is the strategy will change as you go on. Like let's suppose there is another point that is like something like 170. There is a 70 distance as well. Okay, so let's suppose you had 3 points. So in that case you will not be able to decide on which one to put how much, right? It's not directly possible. So like if you put one over here, then one over here, and then one over here, so then multi-set will contain 50-50 and then 35-35. So you will not be able to keep track of that. So multi-set or greedy ideas on this particular problem will fail. Okay. Now, so the other ideas that Amisha and Shashi has suggested is correct, that binary search on the maximum distance. Okay, so in most of such problems where you have to maximize or minimize things, you should ideally think about binary search to be a potential solution. So let's suppose what is the maximum distance that can happen, like after putting key points. Let's say, can we make it 0, can we make it 1, can we make it 2, can we make it the answer we are talking about, right? This is the answer. Okay, the minimum max, like we want to minimize the answer, but let's say the maximum distance, is this maximum distance feasible or not? Okay, let's talk about just this point. Okay, 4 5 6 so on, right? This is like 4 5 6 so on up to like a large value. Okay, this is the space. Okay, this is the space that we are talking about. We can never make this 0 because it's not really possible. According to the setting of the problem, 0 is not possible. Okay, so you will always be given at least 2 points. So since you can put in like points in the integer, like on integers only, you will never be able to make a distance between 2 points 0 ever. Okay? So is the integer distance 1 possible, 2 possible, 3 possible, 4 possible? This is the space that you are searching in, right? Is this clear to everyone that this is my search space? I'm searching on what is the max, like I'm searching on maximum distance, like is 3 maximum distance possible or not, something like that. Okay, is this possible? Is this clear to everyone? The search space, what is the search space in this? The answer is the search space. Okay, what is maximum distance? That is the search space that we're talking about. Okay, now if we talk about a problem in this, you can note that this search space will follow a monotone property, that okay, I cannot make it in 1, I cannot make it in 2, and I cannot make it in 3, but hey, I can make it that in 4. Like let's say 4 is possible, I can make the minimum distance equal to 4. Okay. Then I can also make it 5, I can also make it 6, I can also make it 7, and so on, right? Is this clear to everyone? This is what you need to identify in this, in a problem, to like see, okay, binary search will work in this. So if after putting k points you can make the minimum distance between, like the maximum distance between any two consecutive points equal to 4, then you can also make it 5. Yeah. So what I'm saying is, the answer, that is the maximum distance, is the search space. Okay, we have to minimize this particular metric, but let's say that is our search space. What are the maximum distances that we can create, okay, after putting k points? So of course very small values would be difficult to create because you will need more points, but let's suppose you can create 4, let's suppose you can create 4 after putting k points. Okay, then you can also create 5, because it is easier to create 5 than 4, right, in this particular setting, right? So this will be possible, this will be possible, this will be possible. So this y and n is, so we define an f of x is max distance equal to, less than equal to some given x, possible or not. Okay, so we will have to check this particular thing if it is possible or not, and that will give us yes or no of a particular point. Okay, and then we will have to search for the first yes. Is this idea clear to all? Can I have some doubts on this one? I think this is the whole crux of this particular problem. Rest is just standard application of like the same idea that we discussed. But once you identify that this answer, like this metric that we're talking about, max distance between two consecutive points, that will not be possible till up till some particular value, and as soon as the smallest value appears, everything after that will be possible. Let's take an example to make this clear. Let's talk about, we have, let's say one at a point 0 and a point at 100. Okay, let's say this. Okay, so let's talk about this particular, just 2 points, and you have k equal to 1. Okay, so now if we talk about, let's say, like you cannot make the distance between these two by putting 1.012, sorry, not 0, 1 2 3, so on, right? These are all no's. You cannot make them 49, but I can make it 50, right? I can make the shortest distance between two consecutive points 50 by putting it exactly in the middle at 50, right? Is this part clear? So this is a yes. I can also make it 51 because I can just shift this particular value to 51, and this distance, this max distance will be 51, right? So once I get this minimum value, everything is after that is also attainable. Okay, so this space is over here a monotone, and hence we can use a binary search over here. Is this part clear? Can I have a +1 if everybody is clear on this one? Now, the main thing is, how do I design this particular function that given the maximum distance x, can I put k points such that the maximum distance is less than equal to x? Is this possible or not? How do I design this function? Now this is the problem that you will have to solve like next, because unless you design this fx, this y and n don't make sense, right? If you cannot even solve this, how do I like put the y and n? So now the question boils down to, like, can I put k points and make the maximum distance less than equal to x, or exactly x, something like that? Okay, less than equal to x to be precise. Okay, can I make it less than equal to x? So let's talk about just 2 points for now. Let's suppose the first point is at a and the next point is at b. Okay, so let's say the distance between them is some okay, something distance. Okay, now I when I'm in check function, I know how many points I have to put at a particular gap. So let's suppose these are the gaps, and I want to make, so initially the gap is equal to distance equal to b minus a, right? Now I want to make this gap less than equal to some x given in the check function, right? We are writing the check function right now. So we have to make the distance between them less than equal to x. So how many points do I need to insert in this gap? So I will put 1 at a plus x. I will put at next plus a plus 2x, so that all these gaps are of x, at most x, right? And as soon as this becomes less than equal to x, I stop, right? This makes sense, because if how many points do I need to insert between a and b to make the gap between consecutive points less than equal to x? That's something we are trying to find out right now. Okay, so now how do I find this particular number? Can somebody like try to find this out? Like, what would be the value of this particular number? Okay, yeah. So ceil of b minus a, floor of b minus a. Okay, a lot of two different values are coming up. How many points do you need to insert? Two functions. Floor of b minus a by like x, and ceil of b minus a by x, right? Any other functions that you're thinking? Okay, so everybody says floor. Okay, so let's talk about one particular value. Yeah, so now you're saying floor, right? Let's say there are like the a is equal to a is equal to 0 and b is equal to 100 and x is equal to 50. How many points do you need? So is the floor giving us the correct value? So what's the then how do we calculate it? So it's not either of them, like both of them are like wrong. Okay, so if I write one liner formula for this particular thing, it should be ceil of b minus a by x minus 1. Okay, this is correct. Now why is this working? Because let's just take two cases. There are only two cases possible. If it's perfectly divisible and if it is not. So let's say if a is equal to 0 and b is equal to 100 and x is equal to 50. So in that case, the answer would be, this would be 2 minus 1, 1. And if a is equal to 0 and b is equal to 100 and x is equal to 49, in this case, the answer would be 2, right? Because this would be, this ceil will give us 3 and subtraction by 1 would give us, okay, yeah, ceil, yeah, explaining that. See, okay. So ceil is nothing but like if it's a fraction, like I think this function, ceil function is quite famous. Uh, so over here, like if we have some fractions and you do a ceil or any number ceil, which means is like if you have a floating point number, it gets rounded up to the next number, and if it's like a integer number, then it gets to the same number. That's the definition. Okay. So this particular function works in both of them. And how do we write ceil in code? So if you, so if I have to write the ceil in code, we can use something like this: b minus a plus x minus 1 by x minus 1. Okay, so this will give us this particular value over here is ceil of b by x by x. So this is an integer division now, and this particular value gives us ceil, because if this is perfectly divisible, then this particular part will get uh, removed from this division, right? Because we know that this is integer division, so this is like a fractional part now. But if it is not divisible, if it even just one more, then this part will come into play and it will like add one to the total value. So this will work as a seal only. Okay, this fraction over here, -1 over here, right? So whenever you want to find seal and floor, don't go into floats and all. You can just use something like this. So floor is very easy. So floor is like just b by a, and seal is b plus a minus 1 by a. So these are the two values that you can use there. Make sense? So now let's quickly look into the coding part of this particular problem. So, for this particular problem, what you can do is you can like, we will have the same particular idea, but we will just write something like this. So we need n and k, right? And we need the array. So we will keep these things in global. Then so where is the fifth point? I'm not sure. What is the value of k? So in this case, we know that low is equal to okay. Yeah, we're going to do that next. So low is equal to 1 and high will be equal to very large value. So the maximum difference that it can go into in this particular problem, let's say, is up to 10 to the power 9. So let's keep that high. Okay. And answer will be equal to, you can keep this any value. You can keep this, like, let's keep this 1e9, because if you don't put any point, it should ideally be 1e9, right? Like the distance at max should be 1e9. So then it will work with the check and it will find out. So you can initialize this answer with anything. It will not matter in this particular problem, because one of this will be yes. Okay. Now this particular part remains the same. We remove this. Later on we will decide based on the check function, and then we will write the check function, right? So now we need to find with the particular like maximum distance, is it possible or not? So what we will do is we will first of all, so they are given n points, right? I'm assuming that the points are sorted for now. Like we can, if it is not sorted, you can always sort the points, right? So but I will assume that okay, it's sorted by default. Okay. Now for the check, let's suppose you need, how many points do you need to insert so that every distance becomes less than equal to d, right? Now for each of the interval in the initial array, like there are n minus 1 gaps present, right? So for each of those gaps, we will have to reduce those gaps to less than equal to x value, right? So the difference in that particular gap is equal to ARR of I minus ARR of I minus 1, right? This is the gap, B minus A. And now we need, how many points do we need? This particular metric, right? This we discussed just now. This is nothing but that. If the gap is diff and the like minimum, the maximum distance possible is x, then this is the number of points that we discussed just now, right? This is the same formula. Okay. And if for all the n minus 1 gaps, the total number of points needed is less than equal to k, then we can make this particular max value, or else we cannot make this max value. Make sense? If sum of the number of points needed in each of the individual gaps to make the distance less than equal to x is less than equal to the number of points applied to us, if this is true, then then it's possible, or else it's not possible, right? Make sense? So based on that, if our check returns true, that means it's possible. So our answer is equal to that particular value, right? Answer is equal to that particular value. and my high will be, I will try smaller values next because we need to minimize the answer, right? Or else I will try higher values. Okay, and then we will print the answer. So we have 4 values and 5 numbers, 5 points to put insert, and then the line is 30, 50, 100 and 170. Then it gives me just 20. And let's quickly look into this. How are we putting this particular value? So you have 30 to 50, then 50 to 100, and then 170, right? So you have to put 5 points. So of course for 20 this will work, because for 20 you can put 2 points over here and 3 points over here to make it 20. But making it so you can put 2 points over here and 3 points over here in between these gaps to make each of the individual gaps to be 20, right? But if you need, so if you just try 19, what will happen is you will need one more point over here in this range, but that's not possible because you're given only 5. Okay, so this is how the binary search will work. Is this clear now, Vikash? Like, the binary search is on a very large range, so I'm not try running it on whole, but the thing is, like for 5 it's possible because it can insert 2 points over, it needs 2 points over here. For 20 it's possible, it needs 2 points over here, but 2 points over here. For even more, the values more than 20 as well, it's possible, but because it will require less than equal to k points. But if as soon as you make 19, it will need at least 6 points. In fact, yeah, it will need exactly 6, like less than, it will need 6 points, but that's not given to us. We have only 5, so it's not possible. Clear, everyone? So then let's move to the next problem. Any doubts on this one? Okay, let's talk about another problem. Okay, so let's suppose you're given 2 different arrays. Let's say you're given 2 different arrays. Okay, let's call them A and B. Okay, so now let's suppose you are doing this particular, so this has size n, this has size m. Okay, so these are sizes. Okay, now from this array what you do is you create a C array in which for all pair of elements from one element taken from A and one element of taken from B, you insert A of I plus B of J into C. Okay, like this particular element goes into C. So C will contain n into m elements, right? So for every element of A, match it with one element of B and add that sum into C. Okay, is this part clear? So C is created by just inserting this n into m possible values into the C, and then we sort this particular array. Okay, sort array C. Okay, now you need to find the kth value in the C. Okay, so the question is, you are given the A and B's arrays and they are size n and m, and for all pair elements from one taken from A and one taken from B, you add their addition into the separate, like you can call array C. Then you sort the array C and then you find the kth value in the C. You need to find out what that value would be. Okay, so how do we find this particular element? So of course, like k, so you need to find the case value. Let me give you the constraints as well. So let's suppose you are given n is less than equal to 10 to the power 5 and m is also less than equal to 10 to the power 5. Okay, So you cannot really create the C array and sort it, because if you do that, then like it would be 10 to the power 10. That's not feasible, right? Is the question clear to everyone? Can I have a +1? So this is an, because unless the question is clear, next things won't make sense. Yep. So how do we find the kth particular values? So over here we need to find the kth value, right? So since we cannot create the value, plot both and then take 2 pointers from A and B and move the iterator on the smallest element until we get k elements. No, that won't work, because you cannot move. Like, how do you decide why we only move on the smaller one like that? So I'm not sure how are you getting like the up to the kth element. So like, let's suppose you are at this particular index and this particular index, and then like if you move them, then how are you counting the k values? Like, let's suppose in final all these elements multiplied by all these elements were up to k, and everything about after that was greater than equal to k, like all their cross products. So how will that get counted? Like it will become difficult. Like a solution similar to that is possible, but like we would not be looking into that for today. Smallest element until we get k elements. So we will have to multiply with the size of elements on which all pairs are getting formed. Yeah, that's feasible, but there is an idea similar to this, but still there is a lot of gaps to fill in this. So we will not be looking into this particular idea. Okay, yeah, that's a good idea. So we will try to search for the value, right? Okay, so instead of finding the kth element, we will try to search for the value which lies in the kth position. Okay, and that value will like lie between minimum sum to the maximum sum. That's correct. So we will search in that range. But how do we design the like the search space so that it works? So let's suppose, yeah, yeah, that is true. So hmm. So that's correct. So first of all, we first of all sort these two arrays. Okay, let's. So from now on, I'm assuming that these arrays are sorted. Okay, I'm not exactly sure what is batches in this case, but let's first like, okay, M2 M3, yeah. So why is A0 plus B of X always like all the elements will be less than this? I'm not getting this part. Yeah, this is what is false, right? So if A0 is, so if A0 is 0 and this is 2 and this is 1 and this is 3, then like if you talk about from A0, it will be like 1 and 3 being created. And if you, sorry, let's take this as 0 and 3. So from this 2, it will be like, sorry, this would be 0 then. This would be 2 and 5 created, right? But these two elements are smaller than these. Like, you cannot say all elements are smaller than this, right? So it will not create batches of M. So is this what you're talking about? I'm not sure this will work, because not all A of X plus B of like A0 plus X will be smaller than the next element's smallest one. Like, so yeah, this will not work. So there is no like it's not batches of M over there. Like, I think Abhijit was also thinking in the same direction. Now that's not working. So yeah, so what we'll be doing is we'll be searching for the kth value. But searching for kth value is a bit difficult. Let me explain you why. Because let's suppose there is an array. So after C is being formed, there are some values, and then there is some. Let's suppose the answer for kth value is actually V. Okay, let's assume that kth value is V. Let's assume. Let's say we know. So we know that at the kth position, the value would be V. Okay, but there can be V before that and V after that as well, right? Like we don't know how many V's would be there in the final answer. No. This, I don't think there is some prefix some involved in this. So let's just directly discuss this one. So now, like, let's discuss this idea now. Okay. So let's say the kth value is V. Okay. But based on just V, we cannot directly find out is V the only, like V is V only present at K or not. If we search for V only, we can get this particular index or this particular index and all, right? So we won't be able to check whether like it's there present at K or not. So we will change this problem a bit. Okay. So we will change it like this. Find the largest element with count of elements less than equal to that. Find the largest element, let's say some X or some V, such that count of elements less than equal to V is less than K, strictly less than K. Okay. So we will try to change the problem into this particular problem. Okay. Find the largest element V such that count of elements less than equal to V is strictly less than K. Okay. Now, if we can find this particular V, we know that the answer will be V plus 1. I mean to say it should not be largest element, it should be largest value. This V might not be present in the array also. Let's understand what I'm saying over here. So let's suppose there is an array 1, 2, 3, 4, 5. Okay, and I want to search for the let's take one indexing only for this particular problem. Okay, let's assume it's one. Let's assume that it's 1, 2, 3, 4, 5, and we want to find the fourth element. Okay, so the fourth element in this case is 4 only. So I'm transforming this into find the largest element, largest value V, such that count of elements less than equal to V is less than K. So if you search for this particular thing in using binary search, what we will get is this particular 3, because less than equal to 3, there are 3 elements, which is less than 4. And if you just go to next value 4, you will get more than K elements. So if you use binary search to find this particular V, which we stated over here, you will get 3, and we know the answer is V plus 1. So in case, let's assume that the array was something like this, 2, 4, 5. Okay. In this case also, if you search for the element, if you search for largest element V such that the number of elements less than equal to V is less than K, that would be 3. Why? Because for 3, the number of elements less than equal to 3 is equal to 3. Okay, and K is also, K over here is 4. But if we try 4, then the number of elements less than 4 will become, sorry, less than, yes, it's a mistake. Yeah, number of elements less than equal to 4 is 4, right, over here. Yeah, so this is not feasible because we know that we can only go up to less than K. Make sense? So this binary search will give us 3. And why is this binary searchable? Because for a particular value, number of elements less than equal to this is strictly increasing. So up till some point it will be all yes, then it will be all no's, because it will keep increasing, and at some point it will cross the value K, and after that every number of elements less than equal to that particular value V will be greater than equal to K. So that will all be no's. Okay, so we want to find this last value, which is yes, and we know the kth element will be this value plus 1. Make sense? Like up till this, it's not still complete. We just found out that okay, if we can find the largest value v such that count of element less than equal to v is less than k, then we know that the answer is v plus 1. Okay, there is still this particular problem left, like how do you find this largest v? But is this part clear or not, this particular statement that I have made over here? Less than equal to v, because understand, right, what are we doing over here? So this is not v, so this v is not same as this v, but what we are trying to find is what is the element, like this, let's suppose this value is x. Okay, so there is x minus 1 over here, x minus 2 over here, something like this. These are smaller elements. Okay, so now if we can find out what is the last element that does not touch k, then we could not push this boundary one step further only because that element was present at k, right? We tried to push the boundary as much as possible, but we should not reach k. So whatever this last element we get, we could not push it to x plus 1 because x plus 1 was present at k, right? Then only like this was not possible, or else my binary search would have found it, right? So that is the whole intuition why are we doing this particular thing. Okay. Now how do we find the largest value v such that the count of elements less than equal to v is less than k? So for that, let's understand how we are doing this. This is also a problem in itself, that given two particular arrays, okay, and a value v given, okay, so we are searching on v, we are binary searching on v right now. Find the number of pairs of elements, like how many elements that you can pair between these two arrays such that their sum is less than equal to v. We need to count that, and then we need to check if that is less than k or not, right? So how do we check this particular thing? So there is like n square number of possibilities over here, right? There is still n square. How do we find the number of values that will be present in C array, like after doing all pair summation between A and B, the number of elements that are less than equal to this particular v value? So for this, we will try to use this sorted properties of the array. So we will first of all sort them if they are not sorted. Okay, so we assume now, so remember I told that we are now assuming that A and B are sorted. If it's not, we sort them. Okay, that's not a problem. Now we need to find how many elements will sum up to value v. Now note that for this first element, there would be some prefix which will, yeah, exactly, that's correct. So for this first element, let's suppose this value is a, we need to find how many values in this particular array will sum up to, let's suppose, some value, at some index the value is x. So a plus x should be less than equal to v, right? So x should be less than equal to v minus a, right? So we need to find the number of elements in the second array which are less than equal to v minus a for the first array, right? So what we can do is we can iterate on the elements of the first array, and we can use a binary search or lower bound or upper bound to calculate the number of elements in the second array. Okay, to count the number of elements with which that element can be paired, so that the sum is less than equal to v. Okay, so if this is a, we will search for number of elements less than equal to v minus a in the second array. So this is the problem that we're solving, right? Find the number of like sums that will give us less than equal to v value that we're trying to count. So to count that, for every element in a, we will search for how many elements in b can it pair with, and for that, since this is sorted, we can easily use upper bound, right? Because this is less than equal to x, less than equal to some fixed value. So we are iterating on a array a, so we know this a value and v value, so we need to find the number of x values in b. So we can use upper bound on the array b to find the number of elements less than equal to this value. Is this making sense? Why is this working? So if you think properly, there are two binary searches that are going on in this particular problem. One binary search that is happening on the original problem, that find the largest value v. Now, when we search for this value v, whether it's feasible or not, we are trying to use this particular property over here that, okay, if we sort them, we can find the pair very easily by using a second lower bound or upper bound or by search and this. Okay. So if the code is not like, if how what we are doing that is not clear, we will understand that in code for sure. But is this particular idea of counting number of elements less than equal to v clear or not? Like, how are we counting? If this is clear, can I have a +1 on the chat? Or if it's not, please ask the question, like, what is not clear in this one? Like, for every element, so what my strategy is, I will iterate on every element in A, and for every element I will find out how many elements in B can I sum up so that the sum will be less than equal to V. Once I get this total count, I will just check whether it's less than K or not. Okay. Is it clear to everyone? Can I have a +1 from everyone? If you're not, please ask the question, like, what is unclear in this one. Anyways, we're going to code this, so just the logic part, not how am I going to do, like, write the code for this, just the logic. If the logic is clear, can I have a +1? Okay, so let me write the code. I think that will make much more sense than, because without codes things are like sometimes difficult to understand. So let's suppose I need, okay, so I'm given two arrays, let's say size of n and m. They might not be of same size. Okay, so I'm given n, m, k, and I'm given two arrays, right? Let's take another array. Okay, so we take the first array, we take the second array. Okay, so let's, just for simplicity, let's assume both are of same size, just for simplicity. Okay, now we will sort the arrays. Yeah, it should be m, but yeah, changing the question now. We will assume that both are of same size. It does not matter to be precise, but you should ideally be careful in the question if it is present. Like, we will discuss this later on once we complete this part. So we will now need to search for the value. So let's say the question says that, like, it can be like, let's just search from 0 to the maximum value that the sum can attain. So that will be nothing but ARR of n-1 plus BRR of n-1, right? Like the largest of two elements, whatever the sum is, that's the highest value that it can take. And in fact, you can even search for, so we are taking it from 0 because you can even take this something like this, ARR of 0 plus BRR of 0, right, -1, or this, and you initialize this with ARR of 0 plus BRR of 0 -1. This is also possible, just to prune the space a bit more, but it's okay in such problems, like, because binary search works in log n, so even if you like just take few more elements, it does not matter, right? And we initialize the answer with, let's say, -1. So whatever the low value is, you take low answer equal to -1 of that, like -1 from low. That works. Okay. Now these three parameters in place. Now we need to write the binary search. So we remove this particular things from over here. Okay, and then we design the check. So now we need to check whether whether a value. So we now need to check whether the value x given to us is the number of pairs getting sum less than equal to x is less than k or not. Okay, so I'm assuming in this particular implementation that everything fits in integer for now. Okay, but in actual question it will not. But let's, for simplicity, assume this. So now for every element in A, what I'm doing is I will binary search on B and like add the number of elements less than equal to A in the B. So what I'm doing is, sorry, we'll search in B, right? So BRR, comma BRR plus N, comma, the value would be X minus ARR of I. because so the element should be less than equal to this particular value, right? Then only the sum will be less than equal to k, less than equal to v, less than equal to x. I mean to say this x is nothing but v. This is particular upper bound minus brr is the number of element which is less than equal to this. Okay, and then we return answer. Okay, return this answer should be less than k. Now note that in the original problem you will have to change these things to, let's keep this, you can keep this boolean, you can keep this integer, anything will work. Make sure that you keep these things in long, because note that how many pairs can there be such that how many total pairs are possible? 10 to the power 10, right? So this sum can go up to 10 to the power 10. So you need to keep these things in long. So be sure about thinking about these things when you are implementing questions. Okay. And then once you have this particular check in place that, okay, can I make less than, so what is this particular space over here? Let's understand this binary search over here. So is a v possible or not? Is some x possible or not? So we count the number of sum. If this is less than x, then we say that it's yes. So there would be some range of x's which will be yes, 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 and then there might be some, like there would come some particular like v value such that when you see that v value, it is no. Okay. Okay. So if you like take the number of elements less than, if you search for number of elements less than equal to v, it will come out to be greater than equal to k. So we know that we cannot go over there. So we restrict ourselves up to n v minus 1, and we say that, okay, whatever v minus 1 we got, like the first n that we are getting is like the correct answer. So you can search your first n. Currently we are doing it in this way, like let's say we search for the last y and y plus 1 is the answer. That's what I'm saying. Okay. So now if this is particular y, now after this particular thing we will have to like print answer plus 1, because that is the value at n, like kth value. And when we get this as true, when we get this particular number to be true, we know that answer is either equal to mid, and we know we need to go to the higher range. So low equal to mid plus 1, or else high equal to mid minus 1, right? So make sure you understand why this particular idea is working, because if you have some particular like range of v's in the array, okay, and like this is the kth position, so whatever value, so if you search for v minus 1, it will be less than k, and if you search for v, it will be greater than equal to k. So then that's what, this is the property that we are using to search for the v value. Okay, make sense everyone? Is this part clear, like what are we doing over here? So don't worry, you will have to implement this in like this problem. These problems would be there on your practice module. So you will have to code this one and get them accepted. So you will get more clarity on how this is working. And one more thing, in case these two arrays are of not same size, which one of the arrays should you iterate on over here to be more optimal? Smaller, right? Smaller value, smaller size, because this gets, the complexity is smaller multiplied by log of higher, right? This upper bound will work in log n, so log of the higher array size. So you should try to keep the log part in the for the larger one, right? So that the complexity is small. Makes sense? Is everyone clear with this particular problem? Can I have a +1? So this is like, again, we are doing something similar to what we did in the previous problem as well. So note that what we are doing over here. So we had to search for which element was present at kth position, right? So we were trying to do a binary search on the answer itself, like what is the value of v such that it's the first yes, or v minus 1 is the last yes. Okay. In the previous problem as well, we were trying to do what is the answer which we are searching. What is the binary searched answer that we can make? Can we make that answer or not? So if in a problem, if you know the answer, it's easier to and if it's easier to check whether that answer is feasible or not, then that potential problem is like a good, like uh, that problem can be like good one, a good take for a binary search idea. Okay, so like binary search on the answer, and once you know the answer, you need to just check whether that answer is possible or not. So just use a binary search, right? So let's quickly look at one more problem. We might not be able to solve it completely, but let's quickly look at one more. Okay, so let's suppose you are given a particular, so you are given an array, and you need to find, so you are given an array A, and you are, this array has size n. Okay, you are given a k as well. Okay, a k parameter is given to you. So this array contains some zeros and ones. Okay, so now it's, you can flip any k number of bits in this array. So this is like a bit array, so you can flip zeros to 1, and you can flip 1 to zeros if you want to. You can, you have to flip less than equal to k number of positions in this array, and after that the longest continuous chain of ones would be the answer. Okay, so you need to maximize the longest chain of ones in this particular array after flipping at most k number of uh, positions. Okay, so flip at most k number of positions and then find out what is the longest array possible. So that's what you need to find. Is the question clear to everyone? So given a binary array, like score of the array is like, the score array of the array would be like, is the length of the longest continuous subsegment containing only ones, right? So find the maximum possible score that you can create if you can change at most k elements of the array. So how would we do this? Any ideas? Nice. Binary search on score. That's correct. So we need to find score, right? So let's just binary search on the score. So if you are searching on binary, why are we able to do binary search on the score? Because it should not be one n possible. Hi, the answer can be from, like, let's suppose 0 to n, right? No, it should be 0 to n, because let's suppose k is equal to 0 and all array is 0. So in that case, yeah. Okay, so it will be from 0 to n. But the thing is, how do we check that, okay, whether a particular answer is correct or not? So note that if you can, using k flips, if you can make longest x segment, you can also make x minus 1 using k, right? Because like this is worse than this, so you can, if you can make x, you can obviously make x minus 1. So this space is a monotone space that, okay, like from 0 1 2 3 up to x, everything will be y, like it's possible, but after x, like this is whichever is the maximum length, after that x plus 1, everything will be no, right? So this is a monotone space that we're talking about. Now how do we search for the longest range that you can create? So if we, so now we have binary searched on the length, right? So now we know which length to check. So we need to find out, can we make some length x in the array which has all ones using k flips? So how do we do that? So check every, so if you're checking for some length x, check every segment of length x, right? There are only order n number of segments that are of length x, right? Check every length of, every segment of length x. You can do that. So check for every segment length of x, and check that if any one of them can be made, if any one of them can be made all ones, then you're good, right? Is this clear to everyone, that we can check for every length of uh, length x that we are searching on in binary search? So once we know this, by like using binary search, we are saying that can I make length x or not? So for the check function, we have to check all the segments of length x, right? So for every segment length of x, you have to check, can I flip the zeros and make all of them one? So basically the problem boils down to, is there any range in this array which contains less than equal to k zeros of size x? Like, is there any segment of size x which contains less than equal to k zeros? In that case, we can make x, right? Is this clear? This is what the check would be. And how do you write this efficiently? One way would be like, I think what Amisha is suggesting is keep a prefix sum, and then you can find the like number of zeros in any segment very easily, right? Because you can either build a prefix sum on ones, and number of zeros would be the length minus number of ones, okay? Or you can even build the prefix sum on number of zeros only, right? Also, you don't actually need prefix sum in this particular problem. What you can do is you can maintain a window kind of thing, that okay, I have the like find out the number of zeros in this range, and as I move to the next one, like remove this element and add this element. Like if this is 0, decrease the count. If this is a 0, increase the count. That's it. Make sense? Right? So like you can keep sliding this window easily. Like you don't need prefix sum and all things to put this particular problem. Okay? So just slide the window one by one, and every time you get, like if you're removing a 0, you maintain a count of 0 basically in the range that you are meant, like sweep, like window that you are moving forward, and you can easily maintain the count of zeros with that, because there are just 2 elements will be changed, so that changing will take order 1 only, right? So then with this you can like find out the answer uh, in order. So the binary search will part will take order log n, and for every check you will need order n to check whether that length is possible or not, right? So this would be order n log n. Is this part clear to everyone? Can I have a +1 from everyone if this is clear? Okay. So I hope by now you must have got a good idea of how to basically think for any problem, whether it's a binary search problem or not, right? Okay. So I think it's already some time. We don't have time to start a new problem. I had one more in mind, but that would be difficult, and I think that will take maybe 20 more minutes. So let's just skip that one. So I think we will keep the session up to this, but make sure that you understand how, like, I personally feel that the thing that you should like keep a check on when you are implementing a binary search problem is these things: that how do you assign. No need. The questions that I had discussed today, as well as the question that I was going to discuss, those are all available on the platform. So they will be available on the practice section for binary search. Okay. In fact, this problem is also available, okay, that I discussed just now. So whenever you are writing a binary search, make sure you write the lows and highs correctly. Make sure you just check once that initialization of answer is correct or not. How do you check if it is correct or not? Just check that if your answer is never updated in this binary search, what should your answer be? Just initialize it with that particular value, and that should work. Okay. If this is correct, make sure you are moving the pointers correctly, like based on whether it's a yes no problem. Like it will depend on how the space is, like it's y or n, and then whether you need to find first n last y, something like that. So based on that, this will change. So make sure you understand that first, and then write it accordingly. And then of course you need to design this check function. And of course don't forget to like think about the time complexity. Like don't write binary search if like this check function is like order n square, right? Like if this is even log n, this might be n square and you might not get it AC, right? So make sure you like decide on how do you design the check function. So in binary search, the only like I mean to say the creative thing that you will have to solve is like solve another problem in this check function. So that's where the problem solving comes in, right? Like if everything is standard, then there is no problem solving in this. So this is what you will need to design. Apart from that, this is the like follow this format, and I think you will not get any like big errors due to formatting. Okay. A lot of people struggle with formats of binary search. So even if you know some other format, try to follow this one, because at least it is quite well tested and it does not gives like infinite loops and other things, right? Okay. So I think then we will keep the today's session up to this.